Hi, everybody, and welcome back to Chemical Principles. For the first time, we have fallen just a wee bit behind. Mostly the reason we fell behind is because there's a couple of topics I forgot to cover, a couple of terms from solutions. Won't take long to catch that up. They are terms that are frequently misunderstood and misused. So we're going to talk a little bit about those today. But then we're going to talk about my favorite subject and most students' least favorite subject, thermodynamics. We'll get into that here in just a minute. But first, let's talk a little bit about those few terms. When we talk about solutions, there are a couple of terms that are kind of relative. When we talk about the solubility of something, what we really mean is how much solute can dissolve in a given amount of solvent. Okay? How much solute can dissolve in a given amount of solvent. There are a couple things that influence solubility. The nature of the solvent is solute and solvent is one that we've already talked about. Like dissolves like. Polar solutes tend to dissolve in polar solvents. So the nature of solutes and solvents influence solubility. Something else that influences solubility is temperature. It's not always what you think. Often solubility increases with increasing temperature, but not always. There are some situations, some solutions where solubility actually decreases with increasing temperature. It does exist. As a matter of fact, when gases dissolve in liquids, well, like the carbon dioxide in my Diet Coke here, solubility actually decreases with increasing temperature. The higher the temperature, the less gas can dissolve. This means that for fish breathe water, but of course, what they're really doing, their gills are separating out the oxygen, dissolved oxygen from the water. This is why we drown. We don't have the gills. But what happens is when it's really hot out, especially in shallow lakes, when it's really hot out, the solubility of oxygen decreases. That means that the oxygen concentration is highest at the surface level of the lake. Because the oxygen is right here, it's just not getting into the water. So what ends up happening when it's really hot out, the fish will naturally gravitate to the surface and will be very near the surface of the water. This is why when you're fishing in the summer, it gets too hot and the fish don't really want to do much. They're not getting enough oxygen. They're not real active, and they're near the surface of the water trying to get more oxygen. Relative to solubility, there are three terms I want to talk about. Unsaturated. If it is unsaturated, you are not at the maximum solubility. Okay, not at the maximum solubility. You have dissolved some solute, but you can dissolve more. That's unsaturated. You can dissolve more solute. So you've started to dissolve some. You're up to the concentration you want. If you wanted to, you could go higher, but you're not going to because you're at the concentration you want. That is an unsaturated solution. If you have dissolved as much solute as possible, you are at a saturated solution. You have dissolved as much as possible. You're at the maximum solubility. This is one of those terms that people misunderstand because they confuse it with what is called supersaturated. The easiest way to make a saturated solution, I bought for my friend, and this kind of stuff, it's available on Facebook, not Facebook, on online shopping. I bought this chemical for a friend of mine, cobalt 2 chloride. It's an indicator. Cobalt 2 chloride is pink when it has moisture. It is blue when it does not. So you take a little bit of cobalt chloride, you dissolve it in some water, and you can paint it on something. When it's really hot and dry and there's no humidity in the air, it's blue. When the humidity is high, when it's getting ready to rain, it turns pink. It's a natural humidity indicator. And if I wanted to make a saturated solution of my cobalt 2 chloride, I would put cobalt 2 chloride in water until I had crystals left. Okay? I would put it in there until some of the solid simply does not dissolve. Now, what happens here is now you know the solution is a saturated solution, because if it's not, more of those crystals would dissolve. So those crystals will keep it a saturated solution. And as the temperature rises and falls and solubility rises and falls, it doesn't matter. It's going to stay saturated because those crystals are either going to grow as solubility drops or dissolve as solubility increases. And as long as there's solid in there, I know that solution is saturated. People think this means supersaturated. It does not. It is a heterogeneous mixture because you have solid and liquid. But if you extract the liquid off, leaving the solids behind, that's a saturated solution. It is not supersaturated. Supersaturated is an unstable system. It literally means more has dissolved than possible. More dissolved than possible. Supersaturated is an impossible solution that exists. All right. This may not make much sense to you. If it's impossible, how do you get there? Okay. Let's assume, because I'm pretty sure it does, let's assume the solubility of cobalt chloride increases with increasing temperature. Most solids dissolving in liquids, not all, but most solids dissolving in liquids do have increased solubility with increasing temperature. So here's what you do. You make a saturated solution with excess crystals in the bottom. You heat that solution up to a point where all of those excess solid, all that excess crystal, you heat it up until it is all gone. That's critical, till it's absolutely gone. Now, you're still not supersaturated because the solubility is higher. You've just dissolved the crystals. Now you cool the solution back down. As it turns out, in order for crystals to form, they need something to form on. They can't just spontaneously crystallize. They need something to form on. Same thing with bubbles. If you've ever had a drink, and I don't know how many people still do this, if you've ever had like 7-Up in a glass, or just a regular drinking glass, and you may notice that all of the bubbles is a steady stream of bubbles all coming off of one spot on the glass, just That's where the bubbles are all originating. We call that a seed point. Just like with solids, dissolved gases need a place to form to become gas again. So this is a supersaturated solution of carbon dioxide. There's too much gas in here. That's why it fizzes. All that excess carbon dioxide is trying to come out, but it needs a place to form. It needs a seed point. Same is true for solids. So if you have a very smooth glass container with no seed points, it has to be very smooth, very well made. We're talking laboratory grade glassware. We're talking a beaker or a flask. You get that solution, you saturate it, and then you cool it back down. Now you have a supersaturated solution. If you take one crystal and drop it into that solution, all that excess solid that's not supposed to be dissolved is going to precipitate out. It's a beautiful thing to see. It's gorgeous. So a supersaturated solution is unstable. Sometimes just jarring it a little bit will cause those crystals to drop out. But that's what supersaturated means. A supersaturated is unstable and should not exist. So when you say supersaturated, you're probably not using the term correctly. Saturated, if you have excess solid, that's just saturated. That's all it is. It's not supersaturated. Okay, and that wraps up solutions, which is an interesting segue into thermodynamics. There's a couple of different ways you can teach thermodynamics. You can teach it as a series of equations in mathematics, and here's how you figure out if a reaction occurs or not, and blah, 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 blah. It becomes quite tedious. But thermodynamics are the set of laws by which everything happens. And I mean everything. I'm not talking about chemistry. I'm not talking about science. I am talking about everything. If it happens, it must happen according to the laws of thermodynamics. I used to challenge my students. If you're in love, love has to occur according to the laws of thermodynamics. Love occurs in the brain, and the brain works on chemistry and physics. It works on electrical impulses and nerves and chemicals like oxytocin, which is the love hormone. There's an actual chemical change in your brain that occurs when you're in love. That's chemistry. And chemistry occurs according to the laws of thermodynamics. So if you're in love, that love satisfies the laws of thermodynamics. In every one of these laws. In fact, I'm thinking maybe one of our topics in special topics, if we have any days left, maybe we'll talk about where those holes are in science. I told you that we package science up like it's a neat little package with no holes in it. But there are holes. There are big gaping chasms in what we have. Maybe we'll talk about some of those in one of the special topics. When we talk about the laws of thermodynamics, we're talking about classical thermodynamics. These are the laws that you and I live by because we are classical beasts. It is based on Newtonian physics, which is macroscopic scale physics. I often wonder if, as you get to very, very large systems like the universe and galaxies, I often wonder if there's a new set of laws out there that we've not discovered yet. I don't believe in dark matter. In fact, quantum theory tells us it cannot exist. So why all these physicists are running around trying to find it, I don't know. Somebody made it up. There's a law. There are laws out there that cannot be explained. They cannot explain the behavior of large scale systems. And someone just said, "Oh, there must be something out there that we don't know what it is." Well, scientists have been doing that for years. The old phlogiston theory held that there was an invisible material that held together the atoms, and they called it phlogiston, and it's been disproven. If they can't explain something, they tend to say, well, there must be something out there. No, it's just that we don't understand it. So I don't believe in dark matter. I feel like somebody used it as a fudge factor, and I'm not going to buy it. But just like for very, very small systems, we discovered that classical physics fails. I expect that for very, very large systems, we're going to discover there's a new set of laws out there that we just don't know yet. That's my hypothesis. I could be wrong. Everybody could be wrong. But we discovered that Newtonian physics fails, and we talked about this when we talked about quantum theory. It fails at the subatomic level. But at the atomic level, at the superatomic level, for larger systems like you and I, we followed the laws of classical physics. And that's what we're talking about today, the laws of classical physics. And in thermodynamics, there are four, actually, depending on who's teaching it, some will say three, some will say five. There are four, the way I teach it, four laws of thermodynamics, beginning with the zeroth law. The zeroth law of thermodynamics. How do you get a zeroth law of thermodynamics? Well, here's what happens. They had established the first two laws of thermodynamics, and everyone accepted them as laws. Now, remember, to be a law, you always start off with a hypothesis. Here's what I believe is happening. Becomes a theory. A lot of people say, oh, yeah, I think that is what's happening. I verified it. Over many, many years of testing, it eventually becomes a law, which means that, is it wrong? Could it be still be wrong? Yes, technically it could still be wrong. But by the time it's a law, it has been tested so many times by so many people that it is accepted as an immutable truth in science. So it's accepted as one of the foundational truths that cannot be changed. We hope it can't be changed, because if there's a flaw there somewhere, then there's a lot that's going to change. It just brings down the whole house of cards. But that's a law. So they had already established the first and the second law, which we're going to talk about. But then somebody said, wait a minute, there's something more fundamental than the first law. And everyone said, oh, we don't want to rename the first law. We want it to be the first law. It's too ingrained now. So how do you get something more fundamental than the first law? It becomes the zeroth law. So it's more fundamental than the first law. And it became a law after the first law. So the zeroth law of thermodynamics. Suppose you have a system. And we're going to insulate this system. Anytime we talk about insulation, we're going to assume perfect insulation. Does it exist? No, but we're talking hypothesis. We're talking hypothetical here. So we have an insulator, a perfect insulator, which means no heat can go in or come out. It's the insulator we want. A remarkably Efficient insulator, by the way, is not one but two styrofoam cups stacked on top of each other with a lid. That is a remarkably effective insulator. If you want your coffee to stay hot longer, ask for a second cup. It's very wasteful. It's bad for the environment, but it's going to hold that heat so much better, because what happens is between the two layers of cup, there's a little layer of air, which acts as an insulator as well. So it's almost like having three layers of insulation instead of just one. Anyway, we have two sides here at two different temperatures. With a barrier between them so they cannot cross. Now, it doesn't have to be a barrier. It could be two different metals. In fact, this is how old thermostats used to work. Now, that old thermocouple were two different types of metals that were just in contact with each other. We'll talk about that again in a minute here. But we're going to assume that temperature 1 is higher than temperature 2. So this is the temperature 1 is the hot side. Temperature 2 is the cold side. Eventually, and you know this, eventually the two temperatures will become the same, right? And thermodynamicists realized that something, they did not know what, something had to flow because it was uneven. Something had to flow from the region of high temperature to the region of low temperature, some quantity of something that they called Q had to flow from high to low temperature. They called it heat. They called it heat. So the zeroth law of thermodynamics simply says heat will flow from a region of high temperature to a region of low temperature until equilibrium is established. We need to talk about equilibrium. So in that thermocouple, heat will flow from one of the metals to the other metal until equilibrium is established, until they're the same temperature. Well, the thing is, different metals expand in heat different amounts. So in that thermocouple, what happens is, as it gets hotter, one of the metals will expand more than the other, causing that thermocouple to bend. These days, they actually hook up electrodes and they measure the electrical potential between the two, because that changes as well. But in those old thermocouples, it starts getting cold, or sorry, well, let's use air conditioning because it's better. It starts getting hot. It's a really hot day. That thermocouple, one of the metals will begin to bend faster than the other and will begin to bend until it makes contact with something else, closes the circuit, and the air conditioner kicks on. As it becomes colder again, that metal will again begin to straighten out. And if it gets too cold, it's going to start bending the other way. So that's all that a thermocouple really is, for the old ones anyway, the mechanical ones. So the zeroth law of thermodynamics establishes the concept of heat. At the time that they did this, they had no idea what heat actually was. They just said some quantity of heat is going to measure until equilibrium is established. What is equilibrium? And yes, there are going to be a lot of definitions here. We say that a system is at equilibrium if there are no observable changes over time. No observable changes over time. Now, those observable changes can be our own senses. So if we pick up that cup of water, well, here I am holding a cup of Diet Coke, bottle of Diet Coke, and it feels cold to me. This sits here long enough, it's not going to feel as cold. That is not equilibrium because over time it's changing. Once it reaches room temperature, I can leave it out all day long and it's not going to change. Now it's at equilibrium because it's at room temperature. We can also observe these changes with instruments. I can put a thermometer in there and measure the way the temperature changes. So instrumentation also works. Doesn't matter how we do it. No observable changes over time. We talked about putting water in a very highly concentrated sugar solution, and we talked about how it takes time for that equilibrium to be reached. So we can taste a little bit of the water at the top. We could take a sample of the water at the bottom and we could taste it and say, yeah, this one is sweeter than this one, not at equilibrium. But over time, the whole solution will reach an equilibrium point, and then it'll taste the same throughout. The sweetener in my Diet Coke tastes the same throughout. It's at equilibrium. It's not changing. Over time is kind of an interesting concept. I had a friend, I don't know what happened to him. I hope he's doing well. I have a friend who's a geologist, and he talks about geological time. Did you know that rocks are liquid? He believes rocks are liquid because given enough time, even rocks will begin to settle. Even rocks will flow and distort with time. Of course, we're talking geological times. That's millions of years. Do we have millions of years in the laboratory to watch a rock to see if it deforms? No, it's not a reasonable period of time. So when we say over time, we're talking about a reasonable period of time. Eventually, we're all going to die in the hot death of the universe. We're talking billions and trillions of years away. If we wait that long, yeah, everything's going to change. We're talking reasonable. We're talking temperature scale, time scales that make sense to us as humans. We're talking hours. We're talking throughout the day. It's not going to change throughout the day. Okay. We're going to discover that every law comes up with a new equation, a new concept, and a new equation. The zeroth law of thermodynamics gives rise to the concept of heat, which we define as Q, some quantity of heat. By the way, today, we know that what heat actually relates to is the speed with which, and we talked about this in the gas laws, the speed with which molecules and atoms move. Molecules and atoms move faster. They have a higher average kinetic energy than at lower temperatures. All right. So at higher temperatures, they have higher average kinetic energy than lower. So now we know what heat actually is. But when these laws were developed, they didn't even know what atoms and molecules were. So there's no way they would be able to figure that out. But what's curious about the laws of thermodynamics is that even though they did not know what was really happening, the laws are formulated in such a way that we really don't have to reformulate them now with new information. We still call it heat. We just happen to know that that heat is related to average kinetic energy. The quantity of heat in a substance, and actually we don't talk about absolutes. We do not know the absolute quantity of heat. What we're actually talking about is the change in heat. As this temperature drops, the change in heat on this side will go down. We lose heat. So the change in heat goes down. While on the other side, the change in heat goes up. It is increasing the amount of heat. So we're talking about the change of heat. Will the amount of heat go down or go up? Well, how much the heat goes down or goes up is related to the mass. That is to say, the more material we have, the more heat it can hold. The mass and here's something we're going to talk about. This is a pet peeve of mine. Times the heat capacity times the change in temperature. The change in temperature. Now, there are actually two types of heat capacity, depending on if you're holding pressure constant or volume constant. Usually we use CP. We use the heat capacity constant pressure. It is related to, and we can actually derive this thermodynamically, but we don't have to in this class. The other possibility is constant volume. As I look at this pen, the volume is fixed, but we're not holding it fixed. We're not forcing it to be fixed. It is, however, an atmospheric pressure. The pressure is fixed. So we will use CP rather than CV in this course. Let's talk about three terms. Heat capacity. Heat capacity is the one I strongly recommend that you use. And I'm going to look up heat capacities here. There's some things that I just don't keep on the top of my head, and I do need to look them up. This is, I think, the first time I've used this book. Heat capacity. In my book, that was talked about all the way back on page 25. Seems very strange. Actually looking for a table of heat capacities. I see a table of density. Well, this gives one. We can use that. That's fine. Heat capacity. Heat capacity has the units. That's not the heat capacity. Has the units, usually some form of heat, which we use as calorie per gram degree Celsius. The heat capacity of water for example, is 1 calorie per gram degree Celsius. This is how the calorie is defined. A calorie is the quantity of heat required to raise 1 gram of water 1 degree Celsius. You take 1 gram of water, which is 1 milliliter, and you raise it from 25 to 26 degrees Celsius. That is a calorie. All right. Here, where does it say? Here, this gives calories here. Now, this is Diet Coke. So the number of calories is 0. Is it really 0? No, it means it rounded to the nearest whole number. It's 0. It's less than half a calorie. So this is 0 calories. This does not provide enough energy to even raise 1 gram of water 1 degree Celsius. 0 calories. But you'll notice a calorie is written in a capital C. A nutritional calorie is written as a capital C, and it is actually 1 kilocalorie. So a nutritional calorie is enough energy to raise 1 kilogram of water 1 degree Celsius, or 1,000 grams 1 degree Celsius, which is about 2.5 pounds. So don't confuse a nutritional calorie with a chemistry calorie. But heat capacity always has units. Looks like my book does not have a table of heat capacity, so I'll have to look some up. This is heat capacity. Specific heat actually, let's look one up. Let's look up the heat capacity of aluminum. So aluminum, according to Google, is 0. Different units. Where am I looking up copper? I don't want copper, I want aluminum. There we go. Come on, erase. Okay, so let's erase this. The heat capacity of aluminum is 0.214 calories per gram degree Celsius. Now notice that aluminum has a lower heat capacity than water. That's because it's faster to heat up. It takes less heat to actually increase the temperature of aluminum. Metals are good conductors of heat, and this is why. Insulators would have a much higher heat capacity than water. Higher heat capacity, the more heat it takes to warm that up, to heat that. So, specific heat. And here's something that some author of a chemistry textbook somewhere did not understand. And it drives me crazy when people use terms they do not understand, especially when they're supposed to be an expert. They should have looked this up. The specific heat is the heat capacity of the substance divided by the heat capacity of water. It's like specific gravity. Density is usually measured in grams per milliliter, although that's for condensed states. If you use gases, it's usually grams per liter or something like that. Specific gravity is the density of the material divided by the density of the water. Just in analogous fashion, the specific heat is the heat capacity of the material So for aluminum, it would be the heat capacity of the material divided by the heat capacity of water. I do not like specific heat. I do not like it with bacon and ham. I do not like it, Sam I am. So what does it do? Why use specific heat? Specific heat is for lazy people. There, I said it. It's for lazy people because you get the exact same number. 0.214 divided by 1 is 0.214, but the units cancel. So specific heat is heat capacity, but unitless. I don't like unitless numbers. It's relative to water. If you're ever given heat capacity, if you're ever given specific heat, add the units, just like with molecular atomic mass. Add the units calories per gram degree Celsius. If you're given specific heat, add calories per gram degree Celsius. Okay? Brings us to the third term, the one that absolutely drives me nuts. Specific heat capacity. If an author of a chemistry textbook that uses this term is watching this video, I am saying this directly to your face. You are a fool. Specific heat capacity has absolutely no meaning because it's a conglomeration. They jam together two terms that they do not understand. Heat capacity has the units, calories per gram degree Celsius. Specific heat is unitless. So what's specific heat capacity? It's nonsense. It's bull. It does not make sense. And if you want to know which one they're using, look at their examples. And if their examples use units, they're using heat capacity. If their examples do not use units, they are using specific heat. There is no such thing as specific heat capacity. And I do apologize. I'm getting a little bit heated and hot under the collar here, but this is very misleading for students and extremely confusing. And it occurs because somebody did not understand what heat capacity and specific heat really means. So if you ever happen to see it, that's what they're talking about. And we're going to take a break here because I need to just cool down. I need to calm. Goose faba. What is that phrase when you're trying to remain calm? Anyway, now you know more than authors of chemistry textbooks. And I'm going to take a quick break, 5 minutes. I will see you back here. We're actually at 10:43. We will resume at 10:48. Calm. All right. It just happens to be one of my pet peeves. So I apologize for my little outburst there. Let's do a real quick calculation, shall we? Okay, screen share. So let's do one of the more challenging types of problems that you might come up with using the zeroth law of thermodynamics. Now, if you're given, now, couple quick comments. First of all, change in always, always, always. And this is by convention. There's not a physical reasoning for this. It's just so that everyone's doing it the same. Whenever you have change in, it's always final minus initial. Change in temperature is always the final temperature minus the initial temperature. So let's assume that you have an aluminum teaspoon. I don't know how many people use aluminum for silverware, but we're going to assume that you do. And your teaspoon is your teaspoon happens to be, let's say, 20 grams. I'm going to use a decimal point there for sig figs at a temperature let's say room temperature, 18 degrees Celsius. Okay. Now, unlike the gas laws, we do not have to use absolute temperature in these types of calculations because we're taking change in temperature. To convert this to Kelvin means we would add 273 to both the initial and the final temperature. When we subtract the initial from the final, that 273 would cancel out. But the big hint, and this is why I like heat capacity better than specific heat, look right here. The heat capacity uses degrees Celsius, so we do not need to convert to Kelvin. But we're putting it in our tea, which is hot water. And suppose we have 100 milliliters. Well, its initial temperature is close to boiling, not quite boiling. Let's say it's 93 degrees Celsius. The density of water, which we never talked about before, the density of water is the mass of the density of a material. It's the mass of the try this again in English. Density is the mass of the material per some given volume, usually gram per milliliter. For water, the density is 1 gram per milliliter. To within actually 5, 6, 7 significant figures is 1 gram per milliliter. I forget how many, but it depends on temperature. It does fluctuate with temperature. If you're doing really precise calculations, you can look those numbers up. So 100 milliliters of water this is only true for water. Different materials have different densities. So if you have a different material, it is not 1 gram per milliliter. So obviously 100 milliliters will be 100 grams of water. Now, if you think about the system here, you have a little teacup here, you have water in here, and you have aluminum. Well, we're going to treat the aluminum as if it's a block. What's going to happen? Heat is going to flow from a region of high temperature to a region of low temperature. So heat will flow from the water to the aluminum. So the heat lost by the water will be gained by the aluminum. The heat lost, so I want to put a negative sign there, by the water is going to be gained by the aluminum. In questions like this is one of the major mistakes that students will make. They will forget the negative sign here. The heat is lost by the water, so it's going to be negative Q. It's going down. Don't forget that. The other thing that students forget, what will the final temperature be? Well, are we talking about the final temperature of the aluminum, or are we talking about the final temperature of the water? Does not matter, because at equilibrium, there are no observable changes over time. When we say the final temperature, we mean at equilibrium, which means if the aluminum is still colder than the water, you still have observable change over time. That temperature will continue to increase until it is the exact same temperature as the water. So the final temperature is the final temperature for both the water and the aluminum. So now, remember, delta T is T final minus T initial. That's delta T. It's equal to the mass of the aluminum, the heat capacity of the aluminum, like this. This becomes our equation. Notice that there's no Q in it because the Q cancels. I mean, the Q is right here. I'm thinking about actually getting a tattoo with the formula for from statistical thermodynamics, the formula for entropy. But I'm not going to put entropy there. I'm not going to put entropy equals. I'm just going to put the formula because that is entropy. So this is heat capacity. This is the heat capacity of the water. I'm not the heat capacity. This is heat. This is Q of the water. On the right side, we have the Q of the aluminum. So we can just go ahead and substitute. So we have 100 grams of water. The grams cancel. We do not know the final temperature, but we do know the initial temperature, which we decided was 93. On the other side, we only have 20 grams of aluminum. With a heat capacity, we forget the heat capacity, 0.214 calorie per gram degree Celsius. And the initial temperature was 18 degrees Celsius. Forgot degrees Celsius here. So degrees Celsius will cancel. And calories in the numerator on the left side will cancel the calories in the numerator on the right side. Now, I'm not going to go through the algebra here, but I am going to give you an answer because I think you deserve an answer. Don't you think you deserve an answer? I think you deserve an answer. Maybe I am going to go through and do it real quick. Different people would solve this different ways. Here's how I would solve it. So we have 100 TF. Whoops. Look, I already made an algebraic error. I forgot this negative sign. So we have negative 100 TF minus 9,300. That is going to be equal to 20 TF. Shoot, I made another algebraic. You know what? Let's do it this way. Minus, come on, there you go. $77. Is that 9,300? Is that right? 93, well, yeah, 93 times 100 is 9,300. All right. Or, since I keep making this algebraic error, I'm going to do it very explicitly. Now we collect the terms. I'm going to collect the terms, but I'm going to do it in sort of one step. If you add 100 TF to both sides, you get 120 over here, but I'm going to put it now. We're not going to do that. So we have 9377 is equal to 120 TF. Our final temperature then, I'm sorry, yeah, will be 78.1. Actually, we only have two sig figs, will be 78 degrees Celsius. Now, again, a lot of algebra there. If you do need help with algebra, I'm more than happy to help. I also happen to have, I don't know if you notice this on YouTube, I have a math course that I put together, again, for a friend who had requested it. It's available on YouTube as well, that walks through basic math. So you can watch that series if you would like. Again, it's set up like a course. She chose the book. It is not a book I would have chosen, but she found it where she could download it online for free, and it worked. It's fine. But you'll find that I cover the basics of math, of algebra, I should say algebra, in that course. So there you have the zeroth law of thermodynamics. And we see the practicality of it. We would not be going through this if it was not practical. There has to be something practical in order for these to be used. And here's your practicality here. This heat, whatever it was, they didn't know what it was, but they could do these calculations. Because whatever that quantity is, whatever heat really is, it flows from high to low temperature, which allows us to do some very practical magic. Sorry, reference to a movie. I've used a couple of terms here. I think maybe it would behoove us, before moving on to the first law, to talk about these terms. The term that I have been using, system. We speak of three things. We speak of the system, the surroundings, and the universe. These laws are universal laws, okay? They apply to something much, much bigger than you and me. So a system is a region of space in which we're interested. It's just a region of space of interest. It can have multiple components. In our previous example, our system was the teacup and the aluminum. Okay, that was our system. That was what we were interested in. It's a region of space of interest. Now, it's kind of interesting that it doesn't really have to be space. When we talk about the laws of thermodynamics, the system can be very, very ethereal. We can talk about the sum total of plant life on the earth. Then the plant life becomes our system. Is it one specific volume? Well, no, it's kind of spread out over a very large area. But now all of a sudden our system is not really a region of space, but rather a collection of objects. So a system is whatever we're talking about. A system is what is interesting to us. A system is what we are considering. The surrounding is everything else. So in that example of the T, and we ignored the surroundings there, the surroundings would be the air in contact with the teacup and the aluminum. It would be the room. It would be the house that it's in. It would be the city. It would be the state. It would be the country. It would be the everything else. That's the surroundings. Everything else. When we talk about insulation in this section, we're assuming perfect insulation, which means it is separated from everything else. There is no exchange of heat or materials between our system and the surroundings. Is that reasonable? No, not really. But it simplifies the discussion, and it certainly helps to exemplify the concepts that we're looking for. So the surroundings is everything that is not the system. The universe then becomes very easy. It is the system and the surroundings. So when we talk about the universe, it is the sum total. It is the system plus the surroundings. It is everything, which sometimes we need to consider. In the second law of thermodynamics, the universe becomes very important, and we'll see why. So we talk about the system, what we're interested in, the surroundings, what it's in contact with, and the universe, which is simply the system plus the surroundings. Let's talk about the first law of thermodynamics. Kind of wish that this remarkable was, I wonder if I could work on it sideways. I can actually, I know how to do that. Maybe I need to do that, give up a little bit of the length so that I have more room to write on the width. Too late now. Okay. I mean, I'm up to, what page is this? Like 100 and some odd? Yeah, we're up to 108 pages. I'm not going to suddenly start a whole new chapter. But anyway, and by the way, you know the laws of thermodynamics. You may not know the names, you may not know which is which, but you know the laws of thermodynamics. You're familiar with it. You know if you put your hand on a hot burner on a stove, you're going to get burned. You know that heat flows from that burner into your hand from a region of high temperature to a region of low temperature. You may not know how to formulate it. You may not know, well, now you do. Now you know the equation, but you know the laws. The first law of thermodynamics is simply the law of conservation of energy. It's the law of conservation of energy. And you know this. You know that energy tends to go in natural systems. Energy goes from high to low energy. You know that a ball will flow downhill, will roll downhill, not uphill. You know that. That's the first law of thermodynamics. Energy tends to go from high to low. In the first law of thermodynamics, and I told you this. I told you this. I told you this. Every law is going to define a new term and a new equation. Energy is the new term in the first law. It's the law of conservation of energy. All right. We also got a new equation. We're going to define energy generically as simply capital E, capital E, capital E. So, why I said that 3 times, I don't know. I don't know. So we're going to talk about, see, that's a hanging, what would that be? That'd be in music, that would be called a hanging note, where you're anticipating another note and it's just not there. That's a hanging note. You were expecting me to say it one more time and I didn't. So anyway, it adds to the drama of the course. Are you all dramatized now? Change in energy. It has been demonstrated that the change in energy is equal to the change in heat. Pardon my voice, puberty, plus the change in work. Heat and work can be exchanged. And you add the change in heat to the change in work, and you have total energy. This was actually done by Joules, for whom a unit, the Joule energy unit, has been named. He built an underground laboratory with a huge vat of water, insulated as best he could. With a thermometer. Okay, so you have basically this rod with a paddle in a vat of water. Above the ground, he hooked this up to a harness where we had a horse walking in circles. Why exactly I decided to write the rear of the horse, draw the rear of the horse, I do not know. Except I do know there are more rears of horses on the road today than there are horses. So anyway, that's an old thing my dad used to say, except he didn't say rear. And the horse would walk around. So by measuring how many laps and knowing the distance of a lap, he knew how much work was being done. And as the horse walked, that paddle rotated and stirred up that water, and it heated up the water. So we could measure the exact amount of heat per the amount of work done. And he's the one who actually formulated this equation. Now we already know delta Q. We know that. What is work? I have an old teaching injury. We talk to our physics friends, they will tell you that work is equal to force times distance. I have a bum shoulder. When I taught chemistry at Dakota, well, where I used to teach chemistry, they used to have a brick wall. Sure, they still do in the lecture hall. And I try to be animated because a lot of people find chemistry dull. I don't know why. I love it myself, but that's just me. Different strokes. So when I talked about work, I would talk about force times distance. If I am carrying grocery bags, I'm one of those people that will carry every grocery bag I have because I know enough physics to realize that carrying everything in one trip is less work than multiple trips. Yes, that one trip is going to be more challenging, but it's still less work overall because the distance is less. I only have to walk that distance once instead of 3 times because to and from, or 5 times, or what have you. So to make a point, you can apply a force But unless something moves, there is no work done. So I would literally fling myself against that brick wall, hitting my shoulder with it, to demonstrate. I just applied a force to this wall. How much work was done? Well, no work was done because there was no distance. So the amount of work done, or the change in work, usually the force is constant times the change in distance. And I flung myself against the wall one day and something went snap and it wasn't supposed to. And I ended up with an injury that to this day, this shoulder still bugs me. In chemistry, the force we usually use is pressure. Because recall, pressure is force per unit area. Volume is area times distance. So in chemistry, work is pressure times the change in volume. We see this a lot. I have a tire that seems to have a very slow leak. So what do I have to do? Every once in a while, I need to fill up that tire. And as I fill it up, the volume is expanding. Actually, the pressure is changing as well. Actually, the correct formula would be delta P times V times V times delta V, delta P, blah, blah, blah. Anyway, change of pressures also work, but for this course, we're going to assume it's change in volume. That's work, which if you're using a hand pump, you know that's work. If you're using an electrical pump like all of us do, well, then it's not so much work. Then it's just, well, the work comes in the pump. The pump is using electrical power to do the work. So we have this. For the law of conservation of energy, the law of conservation of energy means change in energy is equal to zero. Now, you have to be a little careful here because can you change energy of a system? Well, yes, you can change the energy of a system. We could put ice cubes in our drink and cool it down. That is changing the energy of the system. So the energy of the system is not necessarily zero. The energy of the surroundings is not necessarily zero, but the energy of the universe must be equal to zero. The energy of the system plus the energy, change in energy of the system plus the change in energy of the surroundings must be zero. The law of conservation of energy. It's not the conservation of energy of a system. It is not the conservation of energy of the surroundings. But it does imply that for any process, anything that happens, any process, if we change the energy of the system, that energy has to come from the surroundings. Is I change the energy in my tire by filling it up. The energy for that change must come from the surroundings. And it's coming from, honestly, it's coming from the battery because I'm using an electric pump that plugs into my battery. The energy for the battery is coming from my house because I have a hybrid car, so I plug it in to charge up the battery. The energy from the house is coming from the power plant. The energy from the power plant is coming from the fossil fuels. The energy of the fossil fuels comes from the surroundings, comes from the coal, comes from gas, comes from all of that. So that is the law of conservation of energy. That is the first law of thermodynamics. We're going to do a real quick example of this probably next week. But for now, we are out of time. So I hope you've learned something. Don't be late for your next class, and I will see you next week. I am out of here.